Hello, everybody. Today I will be solving problem 3.40 from Griffith's E&M book, 4th edition. And so this problem states that two long straight wires carrying opposite uniform line charges plus minus lambda are situated on either side of a long conducting cylinder, shown in figure 3.39. The cylinder, which carries no net charge, has radius r, and the wires are a distance a from the axis. Find the potential. And so they give the answer in the book, but we're going to justify our way to it. So I've redrawn the figure in two different configurations. This top figure here is if we weren't seeing it face on from the x-axis, but we'll be using this figure over here primarily. And so what I've drawn here is we'll be using the method of images to find the potential. And so to do that, I placed two image line charges a distance b away from the origin. And here we have a plus lambda and minus lambda. And so these line charges have been placed here as they satisfy the boundary conditions set by the long conducting cylinder, which is that it is the potential equals 0 on its surface. So we will find the potential at a point P here, point P, and we draw these scriptar vectors to the potential from each line charge. And so here we've called them S1, S2, S3, and S4. And so to get a better sense of what these vectors are, I've written them out here. We'll be using their magnitudes later on, shown on this right-hand side to solve for the potential. So the first thing we want to do is set up our potential, and to find that we'll be first focusing on this positive line charge. And so the potential is given by V equals the negative integral of the electric field dotted with an infinitesimally small length. And so we need the electric field then, provided by this line charge. And so we'll be proceeding using Gauss's law. And so for this long line charge, we'll be placing a Gaussian cylinder around it. And this Gaussian cylinder is of length L. And so there are three faces here. And Gauss's law states that the closed surface integral of the electric field dotted with a differential, infinitesimally small differential area equals the charge enclosed, Q enclosed, over epsilon naught. And so a couple things to note about this configuration. Since we're solving it in cylindrical coordinates, if we take any two electric field vectors, we'll note that the only component that E, the electric field, has will point in the S hat direction, as the other components will cancel out. So the electric field only has an S hat component. And so we'll note that any contribution for the Gaussian cylinder from the right or left face, if we dot it with our electric field, those will go to 0. So the only area we have to focus on will be on this curved area here, where dA and S point in the same direction. So solving for this, we can write the electric field, the magnitude of the electric field. Due to symmetry, the electric field will have equal contribution from where we're standing in the Gaussian cylinder. So we can write the magnitude times the area of the curved surface, which is 2 pi s, times the length of it, equals lambda times the length, which this Q enclosed is lambda times length for this Gaussian cylinder over epsilon naught. And so solving for that, we have our electric field equals lambda over 2 pi s times 1 over epsilon naught, pointing in the s hat direction. And so now we can find the potential, and we'll note that we cannot use a reference point of infinity for our wire because it is long, so the electric field will have an equal contribution at any point we choose. So instead, we'll set the reference point at some s naught, and then we can solve using the equation. So from s naught to s, we have this integral here, and the only component we'll be solving for is in the s hat direction. And so dotting these two together will be 1. And then solving our integral, these are constants. And so the only thing we'll have is from the integral natural log of s prime from s naught to s. And so plugging this in, we have this here, and then due to logarithmic rules, we can write it as such here. So this is our potential for that line charge we focus on up here in our configuration. But we'll note this potential is the same for every other line charge, but the only difference will be in their denominator, their reference point. So for our system, using superposition, we can add our potentials up. So for each one here is from the first one as the magnitude of the vector S1 over A, S2 over B, S3 over B, and S4 over A. And so to note the different values there's different values on the bottom because we are using for this configuration, we are using the origin as the reference point, and each of these line charges are a different distance from the origin, so we have to note that. And so that is taken care of by our formula here. And so we'll go through a little bit of algebraic steps to better to look like the solution given. And so we'll be using logarithmic rules. We'll be pairing this up with this value and this value here with this one. And so using log rules, we can pair those up such as this. So the distances are canceled out. And then we have the magnitude. So we will plug those in here as shown. And then we can get rid of these square roots by taking out the exponent, which is 1/2, and putting it down in front. We could take out this 1/2, and so our solution here will be shown here. However, we need our solution in terms of these cosine phi and s and a. And so right now what we have is y and z with b here. So we first need to solve for these variables. So first solving for b, we have this configuration here. And so I've redrawn it. Two things to note is that the distance from this line charge here, this imaginary line charge minus lambda to lambda is a minus b, and then half of that is a minus b divided by 2. And so we'll define that distance as y naught. And so using the results from problem 2.52, part B, there is a relationship there that states that a squared prime equals y naught prime squared. minus r squared. And so for our purposes, for our problem, a prime equals a minus b over 2, and y naught prime equals a plus b over 2. And so plugging this into this equation here, we have this. And so using some algebraic steps, we'll distribute out the exponent to top and bottom denominators, and we will cancel out this 2 for these parts of the equation, and then here 2 squared is 4, so that's multiplied to the r squared. And so we cancel out some terms here. And then we have this simpler formula for r squared equals 4 times a times b. And so these 4's cancel out. And so what we're left with is r squared equals a times b. And so in terms of b equals r squared over a. And so now we've solved for b. And then as for x and, y and z, from our original diagram, we'll note we have a phi angle here. And so we can define y and z in terms of that. So cosine of phi equals y over s, and sine of phi equals z over s. And so we now have y equals s times cosine of phi, and z equals s times sine of phi. So now we can plug this into the solution we had above right here. And so we do that here. And so the full solution is, I've rewritten it here, given by, once we plug this in here, we'll go through some algebraic steps. So the first one is simply plugging in our variables from y, z, and b here. And so we'll do that. And our next step is to simply factor these equations out since they have the exponents of 2. And so we've simply done that here through algebraic steps. That's all we've done here. And so if we notice, we have s squared cosine squared of phi, and then over here we have a s squared sine of squared of phi. And so we can factor out our s squares, and cosine squared of phi plus sine squared of phi is simply 1. And so we'll notice that throughout our problem, we have this multiple times. And so doing that, we go to this step here. And so we'll note this part of our equation here is now exactly as it should be, but we have to focus on this second term on each the numerator and denominator. And so what we'll do is just a simple mathematical trick. We'll multiply top and bottom by a squared over r squared over a squared times r squared. And so we'll note this equals to simply 1. And so we'll just be doing that. We'll multiply top and bottom by that. And so finally, we get the solution that the book is now looking for, given here. And so that is the solution to our problem, and I hope you enjoyed. Thank you so much.